One way of thinking about calculus is that it's the study of functions. And so what we're going to do is we're going to start the course here by talking about relations and functions. And we're going to see that a function is just a particular kind of relation, a special relation here. So a relation here, and this definition seems a little weird at first, but the technical definition is that it's a non-empty set of ordered pairs. And that just seems kind of strange. But the idea here is a relation is actually relating two things together. Okay, so here's an example. This relation R, what it does is it relates 0 to 1, and then it relates 1 to 3, it relates 2 to 5, and then it relates 0 to 3, and then it relates 3 to 5. And that's this particular relationship, or this relation. And the most basic way of looking at it is you have this non-empty set of ordered pairs where each ordered pair is a different relationship. And there's different ways. Like this is one way of showing relation R, but there's this is not usually the way that you see it done. So another way is by using a table. This is much more common. And so when we work with it, we're almost always going to be working with real numbers, and we're going to be looking at graphs of relations and functions. And so we're going to be thinking of this first coordinate as the x-coordinate and the second coordinate as the y-coordinate, just like in algebra when you graph things. And so the table for this relation would be the following. It relates 0 to 1, it relates 1 to 3, it relates 2 to 5, it relates 0 to 3, and it relates 3 to 5. And so this table is a way of representing the relationship between the numbers according to this particular relation R. Okay, and another way that we can do it is we can use what they call a mapping. And a mapping is where you have like two sets like this, and this first set is like the x, this is the x coordinate, right? And we call that set the domain of the relation. Okay? And this set is going to represent the y coordinate. And this is known as the range of the function. Okay? Now the domain of the function, if I wanted to list this out, is actually the following set of numbers. It's like 0, 1, 2, 0, and 3. And so I'll just put them in order. We don't have to list 0 twice. It's just 0 there, 1, 2, and 3. Right? And that would be known as the domain of the function. And I could put these in here like points, 0, 1, 2, and 3. And now the range of the function, R, and I don't want to confuse it with this here, but when I state the domain and the range, and now I'm already saying function, ain't I? I think I said function, and this we're going to see in a minute is actually not a function. So the domain and range of the relation is a lot like the domain and range of a function. Okay, and so the range here is the y coordinate. It looks like we have 1, 3, 5, 3. And 5. So it looks like it's just 1, 3, and 5. Those are what are in the range. And so I could put 1, 3, and 5. Okay? And so the mapping is just saying, okay, it's going to take 0 to 1, and so I just draw an arrow like that, 0 to 1. And then this ordered pair takes 1 to 3, so I could draw another arrow. this ordered pair takes 2 to 5, like this. And then this ordered pair takes 0 to 3, so I could draw an arrow from 0 going to 3. And then this last ordered pair takes 3 here to 5. So this is going to 5 as well. And so a mapping is just this visual picture, and it's kind of like you're taking these elements in this domain and mapping it onto elements in the range. Okay? And that's another way of looking at a relation. Now, the reason I started with this example is this is the technical definition. When you think of a relation, you know, it's a non-empty set of ordered pairs, and that is to say each ordered pair is relating two elements together, right? And that's the relation. That is what it is. But that's not the way we normally think about relations and functions. Okay? When we work with these, let's see here, we normally think of them oftentimes as equations, right? So this is a particular equation, and now we're going to be bringing in a lot of stuff from like pre-calc and stuff. And so I'm going to try to review as many different little concepts as I can as I discuss other concepts. So if you remember in pre-calc or college algebra, whatever you took, this is actually a unit circle, okay? So it's a circle that's like centered at the origin, and it has a radius of 1. So like this is 1, this is 1 up here, this is -1, this is -1, okay? And so this is a circle centered at the origin. It has a radius of 1. Okay? And so when we think of relations, we're thinking the domain and range are real numbers. Okay? So like even between -1 and 1, of course, there's an infinite number of real numbers. So like around this circle here, there's an infinite number of points around the circle. And it's these points on this circle that satisfy this equation, right? And it's these ordered pairs on this circle that make up the relation that's represented by this equation. So this equation is not the relation. The graph is not the relation. It's almost like the table is the relation, except in this case, because I'm dealing with real numbers, I can't list out the whole table, right? So I could do, I'll just do a few points on here. So the obvious ones here is you have 1, 0, right? Here you have 0, 1. And that's what I should have done here. I should have done ordered pairs. This ordered pair is 1, 0. This ordered pair is 0, 1. This ordered pair is -1, 0, right? And this ordered pair is 0, -1. And those would be the 4 of the ordered pairs in the relation. And I could write it out as a table, right? But this particular relation, because I'm interested in all real numbers, would actually have an infinite number of ordered pairs in there. And the other ones are kind of hard to tell. So let's just try what you have to do to find another ordered pair on this relation is I'd have to solve this. And so I kind of remember about this unit circle that there was an ordered pair that would have like a 1/2. So I'm going to do 1/2 squared plus, so this is where I'm going to let my x be 1/2, right? So I'm going to let my x be 1/2, and then I get y squared, and this is equal to 1. And so then I get 1/4 plus y squared is equal to 1. So y squared is equal to 3/4. So y would be equal to plus or minus the square root of 3/4. And I could write that plus or minus the square root of 3 over 2. Okay, and so I would get 1/2 positive square root of 3 over 2, and then 1/2 negative square root of 3 over 2. So these would be two other ordered pairs, and it's where the x would be like 1/2 here, right? 1/2. And this point here would actually be the positive square root of 3 over 2, and this one down here would actually be the negative square, oops, this is 1/2. And this one would be the negative square root of 2 over 2. So this ordered pair would be positive 1/2 negative square root of 3 over 2. And I could actually do negative 1/2, and up here would be positive square root of 3 over 2, negative 1/2, and this would be negative square root of 3 over 2. And so those would be other ordered pairs. So I could find other ordered pairs, and it ends up there's actually an infinite number of ordered pairs. But this would be an example of a relation. And you kind of see that there's three ways, and we're going to look at this a little more in another video. There's three ways that you can really work with these. You can have a graph. Graphically, you can look at it and see, oh, this forms a circle, you know, and it's between -1 and 1 and -1 and 1, and investigate the behavior that way. You can make a table and look for any patterns in this table. Or, I mean, you can work with the equation. You can manipulate the equation and work on it and study the equation. Okay, and all of these help you kind of learn about the particular relation that's represented by these three things. By this, so this isn't the relation, but they do show the relationship, and it's when it's all numbers where you, if you square the two numbers and add them, you get 1. That's the relation, really. And this circle represents it. It's all the ordered pairs that satisfy that. And this table would be a way of listing out the ordered pairs, but when you're actually dealing with all real numbers, you end up having an infinite number of ordered pairs. And so it would be impossible to list out every single ordered pair. Okay, and it will usually be that way. Okay, so this is kind of just an abstract way to kind of get a handle on it with a finite set of ordered pairs. This is more the way that we work with it. Okay, so now let me show, I have a couple others, and this also hopefully will help you review a few of your concepts. So these are other relationships. These are equations representing the relationship. Okay, and so this is actually a line, if you remember. And what I like to do is I like to solve it for y, right? So, oops, and I'm going to do it in a couple steps. I'm going to move the negative 3x over, and I would get that, right? So I'm moving that negative 3x, and then I'm going to divide both sides by -4. It'd be like this. And then this would cancel out. I would get y is equal to, and then I'd divide negative 3x by -4, and I'd get, the negatives would cancel out. And then I could write 3/4 out front, and then 8 divided by -4 is -2. Okay, and so this is what we're really familiar with. This is called the slope-intercept form of a line, right? Or it's y equals mx plus b. And this is where m is equal to the slope of the line, the way it's tilted, and then the b here, 0b, is where it crosses the y-intercept. So this is the y-intercept. Okay, and so we could graph this then, if you remember how to graph lines. 1, 2, 3, 4, 5, that should be enough. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. And so my y-intercept is -2, so I'm going to start right down here. And so my line is going to cross my y-axis there, but now the question is, well, how is it tilted, right? So that 3/4 tells me that I'm going to go up 3 for every 1 I go over, and I'll get another point on the line. Up 3 for every 1 I go over, and I get another point on the line. And you could keep doing it. Up 3. Oh, and I did it wrong. Sorry. it's up 3 for every 4 you go over. So this is not right. So I'm going to go up 3 for every 4 I go over. Sorry about that. And then I go up 3 over 4, or I could go down 3 and back 4. In fact, that would be like the negative 3 over negative 4, right? Down 3, negative 3, over back 4, negative 4. And there I see my line here. Okay, and that would be the line 3x minus 4y is equal to 8. Okay, and so the slope of the line there tells you how that line's tilted, right? And if the slope is positive, it's rising up, and the bigger the slope, the more it's tilted. So like a slope of 1 is where you go up 1 over 1, up 1 over 1. So if the scales are the same, you're actually going to get this line that kind of splits the quadrant in half, right, with a 45-degree angle. And then if you're greater than 1, you're really steep. If you're less than 1, you're going to be down. But if you're between 0 and 1, like a fraction, like 3/4, then you're going to be more flat. Okay? And then if you're a horizontal line, you have a slope of 0, and if you're a vertical line, you have a slope of 1. And this is going to play a really important role in calculus, because calculus is actually about slopes, but it's going to be about slopes of curves. And a slope of a curve is really the slope of the tangent line, and we're going to be studying those. So this is really important here. So if you need to, you might want to go back and review stuff about lines and make sure you're good on that. Okay, now this looks really strange at first. It's if it were x squared plus y squared is equal to 1, it would be a circle, but it isn't that. Okay? It's some other relation. But one thing I notice here is I can move this x squared to the other side, and I get negative x squared plus 1. Okay? And so this is familiar. So if you've taken college algebra, you know that like y equals x squared is like this parabola, right? Y equals x squared. And you know the negative sign in front of it just flips the parabola upside down, right? Something like this. So this would be y equals negative x squared, negative x squared. So that's an upside down parabola. And then this shifts it up 1. So my actual example would be kind of like, if this were 1, it would be something like this. Y equals x squared plus 1. Now I actually didn't generate tables for either of these actually, and actually plot the point. Well, this one I plotted the points, but for something like this you might want to generate a table. And the tables are just made, it's very easy when they're in this form, when you have y is equal to this, because then you can just put in different values for and I'll go up here and continue my table. 1, 2, 3, 4 maybe. And so you just plug in negative 3 here, and negative 3 squared would be 9. And so you get negative 9 plus 1, and that would be negative 8. So negative 2 squared is 4. This would be 3. Negative 1 squared is 1. And so this would be negative 1 squared is 1 with the negative sign, would make it, so let me do this again. This was negative 4 plus 1, so this is negative 3, sorry. And then this would be 0 at 1, and then 0 here, put in 0 I would get 1, and then put in 1 I would get it would be squared negative, so I would get 0 again. If I put in 2, I would get negative 3 again. Put in 3, I would get negative 8. Put in this, I would get negative 15, right? And so this is like the point where you have, this is the point 0, 1, so that's this ordered pair. This would be like negative 1, 0. this over here would be positive 1, 0, right? And then you could do 2, like at 2 over here, then I'm down at negative 3, negative 3, negative 8, negative 16, so on. Okay, so you can use tables and you can plot points. So if it's set equal to y, it's pretty easy because you just plug in, calculate what your y value is. Okay, I could have done it here. I could have put in different values for x and got out different values for y. And sometimes it's handy because you can pick certain values for x to make it easier to calculate y, or to give you a certain feature on this graph, or just to try to help you figure out what's going on. So you're using the equations and the graphs and the tables, and they kind of all work together to help you work with ordered pairs. Work with relations, which are a set of ordered pairs relating two number. In our case, they're numbers together. Okay, but they don't. A function doesn't always have to be just with numbers. It could be any type of elements. But for us, it'll always be numbers. Okay, well, I haven't defined a function yet, right? So now let's do that. So what is a function then? This is the definition, and this is very important, and it plays so many roles in mathematics. A function is a very special type of relation. And what it is, it's basically a relation where no two ordered pairs have the same x-coordinate and a different y-coordinate. And that's really abstract, but you just gotta, first of all, I would memorize it. My Calc 1 teacher, we had to memorize that definition word for word, and we had to write it on the test. And if it wasn't written exactly word for word, kind of like if you ever done Awanas and you memorize Bible verses, you gotta have the exact words memorized, right? And you gotta quote it from memory. Well, we had to quote that from memory. I'm not going to do that on the test necessarily, but it's a good definition to memorize. It's where no two ordered pairs have the same x-coordinate and a different y-coordinate. So let's look at this first one. Is that a function? So are there two ordered pairs that have the same x-coordinate and a different y-coordinate? And the answer is no. All three of these are different. So you can't have two ordered pairs with the same first coordinate and a different y-coordinate. Okay? And so yes, that is a function. And in fact, I could graph it. Like I could map it here. So I got like 0, -1, 2, and it looks like I got 0 and 5 over here, right? And so this takes 2 to 5. It takes -1 to 0, and it takes 0 to 5. Okay, and so that means this is a function here. No two. These elements don't map to the same. There is no element over here that maps. I shouldn't say that. There's no element over here that maps to two different things. Okay, we're going to see this in a minute. So let's just do this next one here. Is that a function? Why don't you take a look at it and look at the definition? You could even pause the video here if you wanted to and see if you can decide whether that one is a function. What do you think? And as you're doing that, I'll write domain and range. And this is like function f, right? Okay, well, what do you think? Is G a function? And often these are very familiar letters to use to represent our function. Okay, F, G, H, those are the very common letters to use. So is this a function? And the answer here is yes. Okay, because there are no two ordered pairs that have the same first coordinate and a different second coordinate. Okay, it's a little tricky. All the second coordinates are 3, and that's okay. That can still be a function here. It can't be a function if you have an x coordinate going to two different y coordinates, then it's not a function. But you can have multiple x coordinates going to the same y coordinate. And in fact, this one, you have all of these going to this coordinate. And that's okay. That's still a function here. Okay. So now, look at the last one. What do you think? Is that a function? What do you think? Okay. This one is actually not a function. Okay. And let's see why. So it looks like we got 3, 0, negative 3, 0. So it looks like negative 3, 0, and 3 are the domain. And then the range, it looks like is 0. It looks like it's the same 3. Okay, you got negative 3, 0, and 3 for that. And this is not a function because look, I got two ordered pairs right here where you have a 0 and a 0. Two ordered pairs with the same first coordinate but a different second coordinate. And that's what makes it not a function. So let's see what the mapping looks like. So this takes 3 to 0. It takes 0 to 3. It takes negative 3 to 0. And it takes 0 to negative 3. And this is where it fails to be a function, right there. And what you see here is over in the domain, you got an element with two arrows branching off in two different directions. And that's when it's not a function. So if you can only have one arrow going off of these, and if they're all going to the same number over here, that's fine. But if there's a place here where one of the elements are branching to two different numbers over here, that's when it's not a function. Okay, so if we look at the original relation I had, let's see here. So is that one a function? And the answer here is no, because right here, this 0 is going to two different elements, isn't it? So I got an element over here branching off in two different directions. That means it's not a function, okay? Now, let's look at some of these. Let's look at some of the graphs. Would this one be a function? Okay, and the answer is no, because right here I got 0 going to 1 and 0 going to negative 1. Okay, I also have 1/2 going to two different elements. Do you see that? This 1/2 goes up like 0. First, let me show you 0. 0 goes up to 1, 0 goes down to negative 1. 1/2 goes up to square root of 3 over 2. 1/2 goes down to negative square root of 3 over 2. Okay, and so these are like branching. This would be over here 1/2 branching off into two different directions. Okay, now what we get here is, when does a function, or when does a graph fail to be a function? And it's where you're going to have an x coordinate here going to two different y coordinates. And what that means here is that there's going to be a vertical line that intersects your graph in two places. If you have that, a vertical line that intersects your graph in two places, then it's not a function. And they call that a horizontal line test. I'm sorry, sorry, a vertical line test. Okay, if there is a vertical line, and you only need one, but usually there's many, like there's an infinite number of vertical lines that's going to intersect this graph in two places. If there is a vertical line, and I don't want that, that intersects the graph, in more than one place, then it is not the graph of a function. And this would not be the graph of a function. Okay? And we can look here. We got our other example, right? See, this one we have a line here. Okay? And now this line, any vertical line is only going to intersect the graph here in one place. So this is a function. And all lines are actually functions except for a vertical line. Okay, a vertical line does not pass the vertical line test. So this is a function. So what about this one? And the answer is yes, this is a function. Okay, so a vertical line is going to intersect here at just one spot in any vertical line. So this also is a function. So these two are actually functions, and a function you kind of can tell it's a function if you can solve for y and get an equation like this. So both of these here can be solved for y, and we're going to see in a video here pretty soon that if you can do that, then you can actually graph the function on your TI-84 and actually get a graph of it. Okay. But notice what happens here when I try to solve this for y. Let me, maybe I'll do it here. So I'm going to try to solve it for y. I actually have it written out there, don't I? So I'm going to move the x squared over. So I get like 1 minus x squared. Okay, and then I'm going to take the square root of both sides. But when you take the square root, it's plus or minus the square root. So now the y goes away, and I'm going to get plus or minus the square root of 1 minus x squared. And here's where the problem is. It's that plus or minus, because I could put in x here, like I could put in 0, and then I'd get a positive 1. I could put in 0, I would get a negative 1. Or if I put in 1/2, this would end up being a positive square root of 3 over 2 or a negative square root of 3 over 2. So this is a formula that really is kind of splitting this into two functions, right? 1 minus x squared, and this one would be negative 1 minus x squared. And what these actually are is this is actually the semicircle here of the top half. And notice the semicircle is a function. It will pass a vertical line test. And this one ends up being a semicircle here of the bottom half, right? And so if you split this circle into the top semicircle and the bottom semicircle, each of those semicircles are actually functions. Okay? But this is not a function, and that's where it fails. So usually whenever y is squared, it's not a function. Whenever you get the absolute value of y, it's not a function. And there's other things where it might not be a function, but those are the most common. Okay, so I think that covers what I wanted to talk about for relations and functions. And maybe I'll leave it there on that definition of a function. Make sure you know exactly what a function is. It's very precise. Okay, this definition just makes it very, very concrete in a sense. Well, it's abstract. I shouldn't say it's concrete. It's kind of abstract, but it's a kind of, because you have these ordered pairs and you can look at each one, it's sort of a concrete way of checking to see if it's a function. But when we do it, it will be more like these equations involving real numbers and their graphs. Okay, so hopefully this one's probably going to be one of the longer videos because I'm introducing some very, very important concepts here. Hopefully they're a review. If not, hopefully this was helpful and made sense. So, okay, in the next one I'm actually going to analyze a particular function.